So welcome back on this mini series of 2 episodes about exoplanets and the search for life outside of our solar system. Last time we talked about K2-18b, which is an exoplanet discovered in 2015 by NASA Kepler mission, and thanks to recent discoveries and recent observation in 2025, in July 2025 by the James Webb Space Telescope, while we have some hints that life may be present on this planet, which is 124 light years far from our planet Earth, but there are strong signs that life may exist. So let's start about the talk. Today we're going to talk about this exoplanet and other exoplanets that may have and may host life outside of our solar system. Well, thanks for being here. Thanks for listening us on our audio streaming platform like Spotify. But if you are watching on YouTube, you can see also there's amazing animations, there's amazing documentaries, thanks to our friends at JWST. And you can also use our partnership code. And if you wish to have amazing documentaries with scientists and people involved in the actual scientific research, also for life and also other science fields behind the scenes and in-house produced content by directly themselves. So JWST is also producing these documentaries. So you can find original materials, amazing materials also about space and the search for life. If you wish to know more and also to sustain our projects, our channels, use SpaceInfo Club 25, one word, SpaceInfo Club 25 for 25% discovery of our annual plans. So let's start. Today we talk about other exoplanets compared to K2-18b. If you wish to know more about this exoplanet, we have talked about this last time, so you can get our first video and know more about the details of our planet. So just to make a quick analysis of the criteria that we're going to use, we're going to talk about methane and carbon dioxide, which have been confirmed on K2-18b through the observations. And how did scientists make this possible? How do they observe the presence of some chemical substances? Well, we talked about this in the first video, so go and watch it if you wish. Today we talk about DMS again, which is a chemical substance present probably in the atmosphere. We talk about also other planets like the ones that we are going to tell you, like TOI 270d, LHS 1140c, GJ 1214b, GJ 9827d. Okay, so not really some memory friendly words for sure. I am just reading them. I cannot for sure remember them, but what do they have in common? Why are all them candidate for hosting life? Because they are all what can be said to be super Earth or mini Neptune. They have radius between 2 and 3 times the radius of Earth, and also a mass between 5 and 9 times the one of Earth, apart from one which is like 3.5 times the one of Earth. Other things, well, they are all orbiting around a host star, usually a red dwarf, and they are orbiting at a distance not so close to the star and not so far from that star, so that the equilibrium temperature, which is an estimated one, is something like in between -10 and plus 150 degrees centigrade. So okay, last number I say 150 degrees. You may think it's too hot to host life. Well, don't think about life as here on Earth. Life can exist also at high temperatures, but most of all, this is an equilibrium temperature. It's a sort of a medium temperature across all the layers and across all the surface of the planet. As we have said multiple times, think about also the moon. There are hot spots and very cold spots and intermediate temperature spots. But what's the difference between these planets and the moon? Well, you can see if you are watching our video, the atmosphere. There is atmosphere, and like it happens here on our planet, the atmosphere makes a big difference because uniforms all the temperature, and what happens when you have milder temperature, life can exist. But what's the composition of this atmosphere? They all have some common aspects. The presence of hydrogen, some of them has also oxygen, dissociated, atomic molecular oxygens, which have been detected. Some of them also have carbon and also molecular associated with carbon, like methane, CH4, for example. And all of them have habitability potential, which goes from kind of low one, like for LHS 1140C, to high one. And the one with the highest habitability potential is still again K218b, and it's also said to be potentially an ICM planet, something that we have mentioned last time. Today we're going a little deeper in this concept. What does it mean to be an ICM planet? ICM means it's a world containing hydrogen ocean, so a planet that has oceans on its surface, and they are made of hydrogen in most of them. So DMS is formed thanks also to this kind of composition. There is a cycle like the cycle of water, and starting from the ocean there may be bacterial enzymatic actions which produce DMS, which is then associated, chemically speaking, to the elements present in the atmosphere. So you can associate it with the CH3, ammonia if it's present, and then this cycle, it's kind of a simple cycle, starts again. So the DMS goes down in the oceans, dissociates, and bacteria reassociates the chemical compositions, the chemical elements necessary to the formation of DMS. So indeed, DMS is kind of volatile and also can be associated to gases containing sulfur. Also, it's readily detectable thanks to the mid-infrared instruments on board the James Webb Space Telescope. That's why it was discovered. Well, the observations were repeated and made recently thanks to this telescope for sure. So again, researchers argue that ICM planets are defined by liquid water oceans under a thick hydrogen atmosphere. Well, they are arguing about the fact that there may be a runaway greenhouse effect, and in this case oceans can be buoyed away in space. So this is a model, an hypothesis that is still applicable in these cases, but the temperature models also show that if hydrogen rich atmosphere reach 10 and 20 bars, even moderate stellar radiation like the ones of the red dwarfs it's hosting, K218b, can hit the planet to supercritical conditions, and this could make liquid water, unsustainable. Well, another thing is the tidal heating of the planet. The thing here is that the orbital period is kind of small, and the orbital path is more or less circular. So this is one motion to consider. There is another one, which is the rotation of the planet, and the reciprocal gravitational influence between the planet and the host star may attract the not solid, so liquid things, most of all, which are the oceans, and deform the whole oceanic sphere in a way that, combining the orbital motions together with the rotational one, the liquid layer on the surface may be heated up, and this perpetual motion may have apart from circularizing the orbits, may have enhanced so much the temperature to make the whole planet unstable and hostile for life. This is an hypothesis. So how do we classify this planet? Well, there have been detections of methane and CO2. They are strong and also confirmed by the JWST, so James Webb Space Telescope observation to the near infrared instruments. And then there were no detection of carbon monoxide and also ammonia, and this is consistent with the cold trap hypothesis and also the small atmosphere hypothesis. There can be, there is probably more than 10% water volume which is in the interior of the planet, and then DMS signals are below 3 sigma as a level of confidence. So they are inconclusive, they are still tentative, and possibly they are coming from, let's say, the abiotic hypothesis. So DMS can have been generated by processes not associated to life. So what's the conclusion? Well, K218b is a cool, water-rich temperature subneptune, and its classification, so its status, is still ambiguous between Haitian and also mini Neptune, so super Earth or mini Neptune. Today we still don't know what's below the surface, which is the biggest mystery of today. So whether K218b is hosting life is still unsolved. What we know today, it's the most compelling exoplanet for studying water-rich and also potentially habitable subneptune. Today, these are all the information that we know. We still cannot make a conclusive high sigma hypothesis, as we have learned to know today. We'll see how this situation evolves, and I hope you have enjoyed these 2 videos. We hope that you have learned something new. If you want to learn something new every day, go and give a look to spaceinfo.club/learn, where tons of free and premium content like courses are given for free or premium to you. So thanks for being today with us. See you next time.